the thing is, of course, that people know what a spinor is, but it depends on who you ask the question. I am a mathematician, so if you were to ask me what a spinor is, then I would rely on notions from representation theory, I would construct idempotence, I will give you a minimal left ideal, I will declare this is what the spinor space is, I drop the mic, bye-bye, algebra, self-evident. That's how it goes. If you would ask that question to a physicist, then he or she would say it's a column vector. There you go. Now, the good thing is that I actually brought a spinor. This little thing, a USB stick, because if you try to put it into a computer and it doesn't work, then you turn it around, it still doesn't work, and then you turn it around again, and then it works. That is a spinor. Good. Today I will try not to use these technical terms. Obviously, they are part of the story, but I will try to do it in a different way. Now, there is one technical term that I would like to explain because I think it's quite useful to at least know what a representation is. Now, you can represent many things, but today I will stick to groups, group representations, and in particular, obviously, the spin group. I will work with rotors. Now, what is a group? Well, this is a group. This is a finite group. So what is this? That's a bunch of letters. This is algebra. It's just letters. And, well, I would say a boring Sudoku, which represents relations between these letters. This is a group. But my question to you now is, do you know what this is? And the point is that if you want to understand a group, you have to give meaning to the letters. You need some kind of model. And that is what we call a representation. So in this case, I would say that the easiest way to understand what the group is to look at this obscure object, which is the logo of my favorite Belgian metal band, actually founded in Kortrijk. So there you go. So the N, the C, and the A stand for doing nothing, or a clockwise or anti-clockwise rotation, 120 degrees. And the arrow in that table, that is a multiplication, that is just composition. So it's easier to think about the object, I would say, than to think about the table. Now, this is essentially how it works in the world of, first of all, representations and groups. So if you go from left to right, you're dealing with a more concrete visualization. And in the opposite direction, of course, that is more or less the formalization, because it doesn't really matter what object you're considering. The more abstract version, like the global principle behind that, that is the group. But unfortunately, we are dealing with infinite groups. Once again, think of the rotor group. The simplest one would be spin 2, and in a sense, that is enough for today. That's the good news. Now, the bad news is that there's such a thing as the law of preservation of misery. So if you're dealing with infinite groups, then the objects, the pictures that I would like to have, also will be infinite. And the question becomes, what to picture there? Well, I know that this is a GA conference, so thou shalt not mention matrices in vain, but still matrices are very useful here. Matrices, essentially the language of linear algebra, which I would say is easy. Eat that, Morpheus. Matrices are easy. Matrices, that's exactly what you need as a tool in the world of representation theory for groups. So we are dealing with these infinite Lie groups, as a matter of fact, but you can turn them into linear maps, matrices. And that is a very important message that I wanted to get across, that if you have a group and you want to understand that group, properties of that group, it is important to think about the representations, the objects on which it acts as a map, because that will teach you something about that group. And so the first thing I can tell you is that spinors are objects. Spinors are things in a linear space on which the rotors will act as linear maps. So straight away, spinors will teach us something about the group. And obviously the question now becomes, yeah, but what do they teach us? Well, because I use 2D rotors, once again, it will in a sense be enough all the time. Let me just explain to you what is a 2D rotor. And I know that you should know what this is, but the way I see it, that is the following. If you want to make a 2D rotor R, capital R, you have two ingredients, the blue and the red ingredient. Now, the blue ingredient is the most boring thing that you can have. That is the unit. That is 1. 1, as a linear map, represents doing nothing. Everything stays where it was. Whereas B, the red objects, that is a point reflection in the plane. Now, what is a point reflection? Well, you need one point which stays where it was. We call that the origin. And once you fix that origin, you can say that every point goes as drastically away from that point where you can go. In a certain sense, we are working with rotation, so we are preserving the radius, but it's the most drastic move that you can do. It's completely on the other side. I will not go into detail about the black box here. That's just the calculations behind. I know you're scanning it and you're reading it, I hope. But so these are my two ingredients, and if I have those, I can make a rotor. A rotor is just a combination of boringness and drasticness. So this is a rotor. It's a little bit of doing nothing and a little bit of doing something very drastically. But the question is how to fix the constants then? How do I know that I had a proper rotor? Well, we are dealing with groups. And groups have a very nice property that life does not have. You can undo everything. If you did something, you can go back. Everything is invertible. But if you think about it, we have a group element R, a rotor, and if this rotor is not the identity, then the only reason why it is not the identity is because B, the small b, is not 0. So if you want to be able to go back, the only thing that you have to undo is not the boringness, but the drasticness. So hence that minus sign. And then it's a proper calculation. Because we want to undo, so that is like saying that R multiplied with the inverse is equal to 1. And there you go, a sine and a cosine. That is how they arrive in the picture. So what I can do now is to draw a 2D rotor. So the 2D rotor is the red bullet in that picture. It's a point on the unit circle. As a matter of fact, that unit circle that I've drawn there, that is a group. Those are all the elements in my spin2 group. Now we can see that point, we can see that red bullet under an angle T. And I would like to apologize for the following slides, but we need to talk about angles and schmangles. That is not standard. I apologize, but it will be useful for the rest of the talk. Because the angle, that is how you would describe the group element. But if we learn about rotations at school, we always learn about angles. I think most people, if they visualize a rotation, in their minds, they're seeing a classical vector, an arrow, which is rotated. And we think, I can see the rotation. Well, the point is that if you are visualizing that blue arrow, then you're thinking in terms of the schmangle and not the angle. Why is that? And this is why I wanted to talk about representations. You are thinking about the rotation group, the rotor group, in terms of another representation. You are thinking in terms of the representation on vectors in the plane. So the angle in red and the schmangle, which is twice as big, where does that come from? Well, from the typical action. And you know that action. It was presented already many times. Take a classical vector or GA conference, you think, okay, it's a reflection, take it and let the rotor act through the classical sandwich, conjugation. If you then do the calculation, you see where the doubling of the angle comes from. Good. A digression about points. First of all, in 2 dimensions, which is very important for the rest of the talk, the idea is that we take 2 reflections. A reflection is basically a line. You take 2 reflections. Now, they are orthogonal. So uv plus vu is 0. That is the algebraic statement. Geometrically, it's orthogonal. So what you get, B, the product of those 2 reflections, is a point. It's actually the intersection. Now, at the same time, B gives me a point reflection. That is an action. It does something. And I can even use it now to make a rotor. That is boringness and drasticness added. So the symbol B is, in a sense, abused here. Because I would say that it both stands for the point, B is a product UV, but at the same time, I will think of B as a symbol to denote the plane, 2D plane. Yeah, if I do this today, I don't want to kill you. It's just a 2D space. It's a plane. So it's the plane in which this point reflection and the rotations are happening. But now the thing is that if you do the classical tilting action, you were looking at a plane, but you tilt it is actually something that happens in 3D space. Well, then I can repeat the whole story, but some words are changing. So the reflections, U and V, same symbols, are no longer lines, but 2D planes. And they still intersect, and they still give me a product, but now that product is a line. But the line still contains the origin. That was what you were seeing before. Now B still gives me a point reflection. Well, it gives me infinitely many point reflections in all the slices orthogonal to that line. And once again, I will abuse the notation B, and I will say that B not only stands for that line, but it actually stands for a unique point reflection. Unique because amongst all the slices, I pick up the slice going through the origin. That is what I do. If you can make this step, then you can make the step towards the next slide, which is in general. So now, an even number of dimensions for the people who think, how about the odd ones? It's coming. So in even dimensions, U and V still the same letters, but now I have spaces of dimension 2k minus 1. Mathematicians sometimes say codimension 1, counting from the opposite side then. If you do the product, you have a 2k minus 2-dimensional space. But the point, pun non-intended, is that B, the product of U and V, still acts as a point reflection. Now, you have infinitely many point reflection, always in slices. And there's a whole bunch of these slices, but there's a unique slice that I will single out. And that is the slice that goes through the origin. And so in that slice, which is a 2D space, a plane, I can still use the capital B, and it will give me a point reflection, rotors, and so on. Now, I don't know whether you see what is happening here, but this is an inductive process that I'm doing. And I would say that this is really the origin of species. There you go. Spinors. My mind gave me the wrong signal. The origin of spinors. What is the use of a pun if you spoil it? Ah, damn it. Luckily enough, this is not on YouTube, so good. So the thing is that I have decomposed the origin 2 by 2, and 2 is the number of dimensions that I'm peeling off. So I am constantly taking U and V. Technically speaking, I should attach indices, so U1, V1, U2, V2, and so on. So I have these capital BI symbols. These are UV products, but I can also say it's just a point reflection in a 2D space. And so if I do the multiplication of all these B's, and I have K of them, then I have the origin. So each Bj fixes a certain plane. This picture is, of course, completely wrong because too many dimensions, but our brains cannot cope with that. Now, these people would approve with this kind of introduction, Cartan and Dieudonné. Now, on the one side, we have R2K, our 2K dimensional space, in which we single out a very special point. Because this is not always stressed, but when you do rotations, there's always a choice involved for the point that is not affected by these rotations, the center of rotations. So that is a very special point. But at the right-hand side of that equality, and that is the infamous do-re-do principle by Martin Roelfs, we have a natural way to decompose R2K into K copies of two planes, the B1, B2, and so on. So in a sense, this is a very natural way to introduce a spin 2K element, a rotor, via K rotations in a plane. And this is why already a few times I told you it's enough to understand what is happening in spin 2. In a sense, you don't need to know more than that. Well, you need to know this, but then it's okay. Now, what is the point of this orientation? But first of all, and this is important, you can orient a point. The first time I heard that, I was surprised, because I always tend to think of a point as a huge pile of absolute nothingness. So it doesn't feel like you can give an orientation to a point. But again, if you do the tilting principle, then you realize, yeah, it does make sense that you can orient points. Because the point, be careful for your eye, could have been a line, and it's very natural to orient lines if you have a right hand. So it's not strange that we can orient points. As a matter of fact, if I do this decomposition of the origin, then I should think of the capital O as an oriented object. This is not strange if you know about pseudoscalars and determinants, but there is an orientation involved. However, and this is really the crux of the talk, I think, that there are degrees of freedom. For instance, think of 4 dimensions. In 4 dimensions, we have 2 of these planes, B1 and B2. So I can tell you that the origin is B1 times B2. But how about saying that the origin is minus B1 times minus B2? That is literally the same thing, but you cannot see it because minus times minus is plus. Well, here's the thing, spinors can see this. So if I claim that the spinor representation teaches you something about the rotation group, well, I have to say the spin group, double cover and so on. If I say that they teach you something about the spin group, then this is what they can teach you. Spinors can see the difference between B1, B2 and minus B1 minus B2. They can do that. How does that work? Well, first of all, it was already mentioned that sometimes chickens cross roads. So before classical vector, it points towards a point. This is after. And the crucial question here, if you have a point reflection, is how did you cross that road? Did you go clockwise or anti-clockwise? This is the whole point about the orientation. I have been using the word orientation already a few times. Well, this is the reason why orientation enters the story. Because for a point reflection, or you could say when you measure angles, we have a certain choice. You could say, well, you're working in a plane, and a plane is a 2D space. And when I think of 2D spaces, ever since I turned 16 years old and attended a math class, I think of complex numbers. And the most infamous complex number is the complex unit. And it is actually the complex unit that teaches you what the orientation is. Because when we're talking about orientations, then you could say, how did 1 go to -1? Well, there's two ways to go. You can go via the complex unit or minus the complex unit. So that is the orientation being involved here. The plot thickens because now I will associate, in a sense, a third meaning to that capital B. Because I will identify B with a complex unit. I will, in a sense, say that when I orient something, when I choose how I go from +1 to -1, I will go via I, B. That's how I go. That is a choice. That is my orientation. I call that positive, anti-clockwise. Now you could say this is strange. B is not a complex unit. Okay, I agree, but still we have this. If you have orthogonal reflections, then B squared is -1. So this hints towards an association with complex numbers in a very natural way. Does this mean that B is equal to I? Well, a group theorist, he or she would definitely say yes. But the yes is an algebraic yes. The yes is a group morphism. You just send something to something else, and then it's the same. Good. Is it the same? Important question. We'll address it later. First of all, let us go back to CDOD. That's not a disease. That is Cartan-Dieudonné orthogonal decomposition. So we started from an arbitrary rotor now, 2k dimensions, even dimension. You decompose it into rotations in orthogonal two planes. So in a natural way, you are led towards these bireflections, these point reflections. B squared is equal to -1. And what did I do with it? I used it to decompose the origin. And the origin has orientations. Good. Knowing this, let us go back to that picture, because this time, if you get a rotation in 2k dimensions, then we know from the CDOD that actually you have k rotations in two planes. So in a sense, I can draw that same picture where for each of those two planes, I have that circle. And here's the thing, that with my origin here, I can flip an even number of signs. And once again, what a spinor will do is to say that it disagrees with what the lady is saying. The lady cannot see the difference between the origin and the origin in which an even number of signs was flipped. Flipping the sign literally means that instead of taking the blue bullet, you take the green one. Instead of going via +i, you go via -i. That is flipping the sign. So this is the thing, spinors disagree. Spinors can tell you what the difference is. Now, let's first count. You'd say, yeah, you're a mathematician, that's what you like. No, I don't. I count using numbers, letters, not numbers. But so, 2k dimensions, k2 planes, and for each of these k2 planes, I have the orientation, plus or minus. So in total, that gives me 2 to the power k possible combinations. Now, 2 to the power k can actually be put in two different piles of height, 2 to the power k minus 1. There are exactly 2 to the power k minus 1 choices where the overall sign will be positive. So that will be the origin with an even number of flips, and that is still the origin. And the lady from the meme, she cannot tell the difference. In green, I will always use with the minus sign. So green will always be then a negatively oriented origin. Now, for those in the know, these are the dimensions of the spinor space. I already told you that the spinor space is a linear space carrying an action. Well, a linear space has a dimension. This is the dimension. That's where it comes from. What is now a spinor? Well, first of all, there are, in a sense, two kinds of spinors. You will explain that later. But the simplest example of a spinor is basically such an arrangement. Such an arrangement of plus and minus signs. So for instance, in 6 dimensions, k is equal to 3, I choose this here. What is now the point of constructing a spinor? Well, I want to make a mathematical object. I want to find a mathematical object that can tell me whether, for a certain index, I have chosen blue or green. Did I choose the plus or the minus sign? I want to keep track of that. Now, when I say a plus or a minus sign, that is binary information, that is one single bit, but it's not literally plus or minus 1. If you've been paying attention to that circle, in a sense, we already know that the information will be plus or minus I, not plus or minus 1. So what are we looking for? We are looking for, I called it capital phi, the Greek letter, indexed, if you think about it, by a binary code. And if you ask the question, first of all, what is asking the question? That is, are you positive or negative? Then it will give you a number, lambda, and we expect it to be I, with a plus or a minus sign. That is what we would like to construct. So for instance, in this specific situation here, a phi such that if you ask the question, these are the answers. Now, crucial observation here, I introduced a metaphor, and the metaphor is we are asking a question. But how do I turn this into mathematics? Well, apparently, asking a question means hitting it from the left, hitting it from the left with B. So if B asks phi the question, B is multiplied with phi. And that is only a left action. And that might be surprising if you grew up with conjugated actions. Then you think that this is a weird choice. But it's obviously not so weird. Because if you act from both sides, you are destroying plus and minus information. Because a minus and a minus is a plus again. So it makes no sense to do conjugated action if you want to talk about signs. So I consider left action only. If you remember the Angle-Schmangle story, that is where it pops up here. Break, because they asked me for the video guy to do halfway a break. There will not be a proper break, but just we cut it here. And we go to, I think, a tad bit of algebra, easy algebra, but so beautiful if you see it. Well, that is not very objective, but still. B squared is equal to minus 1. And I think that I was 15 years old when I had to learn how to factorize. And I thought I will never use that again in my life. Here I am factorizing things. B squared plus 1 is equal to 0. So B minus I times B plus I is equal to 0. And you can learn a lot from that relation. First of all, just looking at it, you can see that if you hit B plus I from the left with B, you get I. And this is exactly what I was looking for. This is asking a question and getting an answer. And it's the answer that I expected. So somehow, I would like to conclude that I found a spinor. B plus I, as an object, is an object that stores the orientation. Beautiful. Now, we cannot use an equality here. That's why I asked you the question before, is B equal to I? No, obviously not. It's not equal. It cannot be equal. Being a mathematician, allow me to give at least one proof for this claim. So from now on, a spinor, and I apologize to all the physicists who use Greek letters, I use funky symbols. For me, the spinor will be the plus box. Now the plus box, B plus I, cannot be invertible. And why not? Well, imagine it were invertible. If it were invertible, then I can read from left to right that B is equal to I. But that is impossible, because this is a grade 2 element, and that's a scalar. It's a complex scalar, I agree, but this can never be right. So that spinor there, the plus box, cannot be invertible. And I think that this is one of the reasons why spinors are considered to be strange. Because we are used to the behavior in the red box here. If you have two objects and you multiply them, and someone tells you, I got 0, then you're used to think, you started with at least 1 0. But this is not always true. Mathematicians invented words like zero divisors for that. And then if you know matrices, for instance, then you know that this can happen. But this is not the behavior that we expect. So it can be that you multiply two things and you get 0, but what you started from was not 0. And this is obviously a nice example. B minus I and B plus I. Product is 0, but they're both not 0. Now, strange is good. And why am I saying that? There you go. Why am I saying that? Well, B squared plus 1 is equal to 0. You can rephrase it slightly if I introduce the reversion symbol. The reversion symbol acting on capital B gives me minus B. So if I now, like a proper physicist, use the Greek letter psi, then the relation above tells me that psi times psi reverse is equal to 0. And this was announced by Martin, that you have objects which have this behavior. And actually, I like this. Now, why do I like this? Because spinors live in a linear space. Spinors belong to a vector space. Using vector in a sentence is always dangerous, so that's why I prefer a linear space now. But saying that the product is 0 is perfect for linear purposes. Because if you multiply psi with a constant, the constant c, then you expect to end up with a new spinor. Well, once again, if you do that product, the object times its reverse, you still get 0. So the property of being 0 when you multiply is preserved. This is half the story, because if you know linear spaces, then you know that this is not enough. We also want to take sums. This is a detail for which today I have no time, but it will also be okay for the objects that I will construct. Oh, there was something wrong with the animation here. So, is B equal to I? Group theory tells you yes. Geometric algebras, well, they will say no, but. And it's the but that I would like to focus on. Oh, that sounds very strange. Scalars are not grade 2, so it's a definite no, but still, I can tell you why it does make sense to say that B is equal to I. I will talk about spinors as eigenelements, which I think is a word that Martin has also been using. So if you look at this relation, there are two things that you can learn from this. In a sense, you can read it as an eigenvalue relation. You could say, look, B has two eigenvalues, plus I and minus I. So it is true that B is equal to plus or minus I on suitable eigenspaces. Then it will hold. And so I'm just saying now that the problem has been shifted now. The only thing I have to do is to construct these eigenspaces. And you could say, well, you already did that. We're done now. This is a short talk. Because I can ask the question to B plus I, and it gives me plus I. But obviously, instead of looking at B plus I can also look at B minus I. And then I also get the correct answer. So you might think now, we found the minus square. The plus square and the minus square, we're done here. Well, unfortunately, whereas this is true and apparently very useful, this is also true, but not useful. This is not useful if you want to talk about spinors. And I think that answering this question, why not, might be the hardest part of this talk. So if so far you thought, this was easy, then that is very good news, I think. Otherwise, sometimes apparently it's okay to say, look away for a moment. So intuitively, switching from plus I to minus I would say geometrically speaking, is reflecting something. So I need to think about how to arrive at a reflection in my story. For instance, here, my favorite example, I have plus, minus, minus as a configuration of orientations in 6 dimensions, k is equal to 3. And so I have my origin. It's plus the origin, because I have 2 sign flips. Now, what helps me here tremendously is to realize that if I take 2 reflections now, a reflection V2 and a reflection V3, so one in the first and, well, one in the second and one in the third plane in green, then I can rewrite what you can read here in the red box, in the sense that the minus sign is absorbed now into the classical conjugated action. If you were to calculate V2, B2, V2, you would get minus B2. So I got rid of minus signs and replaced it by reflections. Now, as is often the case in these circles, geometric algebra guides the way from now on. Because the thing is, and I will get rid of the index now, in general, B, the bireflection, the plane. If you take a reflection in that plane, and saying that it is a reflection in the plane means that B and then the outer product V is equal to 0, then I can rephrase the left-hand side to arrive at something that you can see at the right-hand side. Now, this is a crucial calculation, so let us see what is the left-hand side. The left-hand side is just the question that I've been asking to my plus box, but I put 2 minus signs. I put 1 minus sign at the left and 1 minus sign at the right. But it is essentially, and that's why I used the blue color here, it's essentially the plus box question. But then the minus sign, I can get rid of it. So minus B is VBV. And then there's only one thing left. I multiply with an extra V. So if you multiply with V from the left, V squared is equal to 1. So that's why you can see a single B now at the left. Whereas on the right-hand side, an extra V was introduced. Well, this is the negative spinor. Now I have an object which you can ask the question, how are you oriented, by hitting it with B, and it will give you minus I. And this time I have an object that comes from a reflection. So this is exactly what I want. So small recap so far. This is a talk about spinors. Well, if you stick to 2D, and in a sense that is enough, then we found our spinors. There is the plus spinor, which is B plus I, and there is the minus spinor, which is taking the plus spinor and reflecting it. That's it. Is V special here? There are 2 slides coming now with some calculations. It's not very important. Is V special here? Obviously not, because it's just a choice. I didn't even bother to give you coordinates and so on. So obviously you can take any V. But the thing is that if you pick such a V, it automatically gives you a certain U, another reflection. I think that is one of the main messages here on the slide. V, choice, U, dictated by your choice. And then I did some calculations. What I did here in the red box is to calculate, if you look at the left-hand side, it's 2 times the same expression. Whereas the right-hand side looks different. I put it in red, but they look different. But obviously they're equal. It's just A is equal, well, not use A and B in this framework here. Something is something else, something is still something else. So they have to be equal. You know your logic laws, right? So, but the thing is that, and this is just the same relations, but on another slide, the thing is that I created something. And when you think of creation, then physicists get all excited because creation and annihilation, that is something very important. Hello, sexy fermion. And it follows from the calculations here. So if you look at this, what can you see here? Apart from the relations themselves, it's not really important. What is happening here? Well, I've got a negative spinor, that's the minus box. I can hit the minus box with something, and then I get 0. Whereas if I hit the plus box with that same thing, I get the minus box. So in a sense, it would be like moving from blue to green, and then moving from green to 0. Annihilation. And obviously, you can also move in the other direction. So I can hit the negative box and arrive at the blue box. Oh, I'm always very anal about my slides. This should have been green and not red. Very sorry. It is important to get your colors right. If this were a traffic situation, we were in huge problems now. But so you can hit the negative box and arrive at the plus box. And if you use that very same operator to hit the plus box, you get 0. So that is creation annihilation. And you can only occupy one state, because if you do it 2 times, you get 0. So this is the connection between spinors and fermions, in a nutshell. Now, dimension 2, it was so useful for everything that I have been saying, but it is so boring. It is, as a matter of fact, too boring. Dimension 2 is too boring. And let me explain why. Because I will now introduce 2 spaces, linear spaces, namely the positive and negative. I have already been using these words, while spinors. This is more the physical language. These are while spinors. But when you do a rotor action, it's a representation, I told you, so rotors will give you something that can act on it. When you do this action, then the positive and the negative while spinors in 2 dimensions just go to themselves up to a factor. So nothing really happens here. Now, an algebraist will say, yeah, obviously, this is an abelian group. But you can ignore this, that is not the point. The boringness is in the fact that we cannot mix up the while spinors. But if you go 1 dimension higher, then you are going from while spinors to Dirac spinors. So what are you doing then? Well, we couldn't go from plus to minus because that is a reflection. That was the point of my construction. My whole construction was take a plus and reflect it. But you cannot go from plus to minus with a rotor because you're using a reflection. Unless, of course, the solution is always easy post hoc, unless you can turn a reflection into a rotation. And that is very easy, just add a dimension. So I was focusing on 2 dimensions, but I'm telling you, do it in 3 dimensions. If you go to 3 dimensions, you have 1 extra reflection. And that 1 extra reflection allows you to see just the reflection as a rotation, because there's an extra dimension in which you can perform this rotation. So this is why SU2 or spin 3 deals with Dirac spinors. You can mix up positive and negative spinors. And this is, of course, when quantum mechanics enters the chat, because instead of looking at the blue and the green box separately, I now have an orange box with Dirac spinors. I have an extra reflection, I called it W, and it allows me to rotate, not reflect, rotate from the plus to the minus box. Now, WV is a rotor, but it's a very special rotor. It's, in a sense, a capital B, but there's too many capital B's here, but it's just a point reflection. But how about we take an arbitrary rotor? So an arbitrary rotor written as an exponential here. If you let that act on the plus box, suddenly you get a weird object. Suddenly you get a linear combination of a positive and a negative spinor. And the question is, what is that? What is the linear combination of a positive and a negative spinor? Spinors, for me, geometrically, are just orientations. So somehow, if you have a linear combination, you are not fully oriented. You didn't make a full choice. Now, I took a few examples to show you what is going on here. For instance, if the t that I plug in the formula in the orange box, if that t is equal to 0, well, then if I do something with the plus box, I just get the plus box. Okay, that makes sense. Or if t is equal to pi, if my rotor acts on the plus box, I get minus the plus box. And this is very important, that you don't feel like you changed the orientation. We didn't do that. A minus sign did appear here, I know, but it's still the blue box. So you didn't change the orientation. However, if you take t equal to pi over 2, well, that is the proper reflection, of course. Now you turn the blue box into the green box. So now you changed the orientation. You went from plus and you did this. But you can go halfway. If my angle t is pi over 4, then I have this equally distributed linear combination of plus and minus. So how to make sense of this? First of all, when that minus sign bothers you, it should not bother you. First of all, if it bothers you, take a square. Then you get rid of it. There we go. Or if it bothers you because the angle is pi, then just switch to the schmangle, because the schmangle is 2 pi, and then nothing happens. Or you just think like a physicist, and you say, yeah, that's all right, it's a phase factor, no worries. This here, does this bother you? Square root of 2 over 2. Square root of 2, does it bother you? It did bother Pythagoras, but it should not bother you. Because if you square that, you get 50-50. Something is really shouting at you and saying that you're halfway between positive and negative. This, to me, is a very important principle in mathematics, and I only thought about this during the preparation of the talk. The saying opposites attract is wrong. It should be opposites are orthogonal. That is what a mathematician does. Opposites are orthogonal in some space. Now we are working in orientation space, aka spinor space. We are keeping track of orientations. And so if you go from the blue orientation to the green one, that reflection, that feels like a rotation over pi, plus or minus pi. But the thing is that if you are thinking this way, you are again thinking in terms of schmangles. You shouldn't do that. You should think in terms of angles. Blue and green, as orientations, they are opposite. So to go from blue to green requires half a rotation. Well, the other one is double, so that is the rotation that you use. So important picture, halfway between a positive and a negatively oriented two-plane means under an angle pi over 4, because opposites are orthogonal. Now, can you do it in higher dimension? You obviously can do that in higher dimension. And once again, this is not too difficult, because if you understand what is happening in 2 dimensions, you just use the power of CDOD. So this time, we have commuting bireflections, Bj, and with each of these bireflections, I associate one extra reflection. One extra reflection, why? Well, I have a plus box, and I want to make a minus box. So the blue one is just Bj plus I, and the green one, hit it with one reflection. What is an arbitrary spinor now in your higher dimensional space? Well, just multiply these boxes. That's how it works. You can give it a name, usually a Greek letter, So I choose the Greek letter phi indexed with the binary code. Binary code, why is that? Again, plus minus. That's what you do. So for instance, k is equal to 5 this time. We're going up in dimensions. So plus, minus, minus, plus, plus. What do? You just multiply the associated boxes. So for 1, 4, and 5, I just use the blue version, and for 2 and 3, I have the green version, which means take the blue version and multiply with that reflection operator. You can even say that if you get rid of all the indices, 1, 2, 3, 4, 5, well, that is the meaning of the blue box at the right-hand side of my equation. Now, I started the talk with what is a representation. So now I can tell you spinors are indeed a representation. So a very easy observation is that a spinor is even or odd depending on the parity of your code. The origin was oriented with an overall plus or minus sign. Now, this leads to the positive and negative while spinors. We already knew the dimensions from before, because we did the counting argument. And the thing is, of course, that if you take a rotor, because it is an even element, and you multiply it with the spinors that we have constructed, you will still be in the space of the positive or the negative spinors. Be careful if you allow linear combinations. That is, of course, very important here. Once again, this is Weil versus Dirac. Rotors cannot mix up blue and green unless you go one dimension higher. If you go one dimension higher, then you have one extra reflection, and then reflections become rotations again. What if you go one extra dimension higher, do, re, do, then you have an extra box. So it's really in steps of 2. Good. Obvious and or mysterious. Spinors. Do you think they're obvious or mysterious? I would say they're obvious. Spinors are obvious objects to me. And I say that having thought about spinors for more than a month now. But it's obvious. It's just orientations of the origin. It's just an object that keeps track of how you orient the two planes coming from CDOD. And it does that by keeping track of plus and minus I. That's the obvious thing. But in a sense, I have to say that these are pure states. These are my capital Phi's with the binary code. These are proper orientations that you keep track of. But they become very mysterious if you allow them to be a representation for the spin group. Because if an arbitrary rotor acts on these pure states, then you can end up with a linear combination. And that is a mysterious object. Because then the question is, what is this? Something that is not positively or negatively oriented, but somewhere in between. What is that thing? Well, this is the point where some people like cats. You have to give a proper interpretation for that mixed situation. And so one of the typical ways to answer the question, what are you looking at, is by introducing probabilities. So a mixed state spinor would be, first of all, the blue phi sigma and phi tau. So let's say 2 orientations, positive orientations, an even number of sign flips. Now you can multiply with an orange number, and the orange number is a phase factor. Now I'm not going to show you the calculations, but I will give you the interpretation of a phase factor. If you take a rotor that acts in one of these planes that you've selected, you are not changing the orientation, obviously, but you're doing something. Something is rotating in that plane. Well, that is what the phase factor keeps track of. So if you're still with me, I had that minus sign earlier, and I told you square it, you get rid of that. That minus sign was just a phase factor. It has no impact on the orientation, but it's still there because you did something. What makes it difficult is the red constants, C1 and C2. And these come from mixing up pure states. So one possible interpretation here is that you say that if you square C, C1 square, C2 square, is the probability of finding your orientation in that state. That's one way to look at it. And what you can obviously do, and this is what happens most of the time, because I think some physicists will think you forgot to take an absolute value, well, a modulus, but the thing is that I will now absorb my phase factor into the constants. That is what usually happens. And so at that point, I have to say that I'm not working with real constants, but complex constants, gamma 1 and gamma 2. But they, in a sense, come from a cosine and a sine, that is rotation, and a phase factor. And now I can still say that the way I look at it is just giving it a meaning as a probability to be in a pure space, a pure state, I should say. And so this means that we have a final recap. And the final recap, I think, is an ode to CDOD, which is the absolute powerhouse of this talk. It is because of this orthogonal decomposition, it is because you can write a 2k rotations in terms of k rotations in a plane, and because a rotation in a plane is oriented, clockwise or anti-clockwise. And that is what spinors keep track of. And that is all, that is very easy until you start taking linear combinations. And then I think it becomes a little bit muddled and you have to switch to cats. Good. I think for me, this is where I am right now. Thank you for your attention.